In the previous class, we saw how we can distinguish a metal, a semi-metal, and an insulator based on their band structures and how the band is filled depending on the number of electrons available per primitive cell. So now we will go on to relate the band structure with transport properties. Now, one of the most striking results of our study of block electrons is that the block levels or the block energy states, they are basically stationary solutions to the Schrodinger equation. That means they just give you a nice eigenvalue, that is the band structure En of k. That means that although you take the electron and put it inside the periodic potential, the lattice momentum will not change because of scattering from the lattice ions, because of ionic scattering, and the velocity, as we saw, is time independent. This is extraordinary. So if that is the case, then how do you get resistance? Because in the Drude model you saw that resistance came because of a very simplistic idea that electrons got scattered off from the ions. But now we are saying that you have a periodic potential and you put an electron, there's no resistance, the velocity doesn't change, there's no scattering, and that's crazy. So your full theory of electrical resistivity is beyond what we can do in this course, but the source of electrical resistance is lattice vibrations. So we shall study about lattice vibrations in detail later on, but what happens is that as you may have guessed, the lattice vibrations strongly depend on temperature. You can think of each lattice site, each ion, as vibrating like a spring, like an oscillator, as a first approximation. So you have an array of oscillators which are vibrating, and because of these vibrations, the periodicity in the lattice will get destroyed. That is, it will get disturbed, to say the least. If it's not destroyed, I can say it's get disturbed. So the periodicity gets disturbed, and at high temperatures the vibrations will be more, and therefore the deviations from the periodicity will be much higher. So these lattice vibrations are responsible for the electrical resistance. So you can say that they are the source of scattering of electrons, and that's what causes electrical resistance. When you cool the solid down, then the vibrations decrease, and naturally the scattering comes down, and the resistance comes down, and the mean free path increases. So that is the source of electrical resistance in a solid, but we will not be quantitatively discussing that in this course. Now we shall look at the features of what is called as a semi-classical electron dynamics. It is called semi-classical because if you are going to consider changes in the electronic wave vector, very, very small changes in the electronic wave vector, that is delta k by small delta k, then you need to consider the effect of the periodic potential. You cannot treat it as a free electron, and therefore you need to use quantum mechanics to consider the effects of that periodic potential, and that's what we did. We solved the Schrodinger equation to study the properties of the block electron and so on. However, that change in delta k in the reciprocal lattice would mean in real space the electronic wave function is spread over several unit cells. So you can think of the electron as a wave packet, the electronic wave function as a wave packet spread over several unit cells, but we shall only consider the influence of electric and magnetic fields whose wavelength, in case they are oscillating, whose wavelength is much larger than the spread of the wave packet. So therefore we don't need to worry about the electric and magnetic fields, the quantum effects associated with that. So we will treat the electric and magnetic fields as classical, and we will treat the wave packet naturally, as the name suggests, quantum mechanically. So that's why it's called semi-classical. So the periodic potential is treated quantum mechanically, but the influence of the external influences, the electric and magnetic field, they are treated classically. That's why it's called semi-classical. So for a given band structure En of k, how does the position and momentum, or I should say crystal momentum or the wave vector of an electron behave under applied electric and magnetic fields without considering collisions? We will not consider scattering of any kind. We'll just assume that the lattice is static. So the velocity, as we saw in the previous class, is basically given by that expression. It's the gradient of the band structure, and we can from this we can work out a simple equation of motion for the electrons for the block electrons. So we can write the change in energy as this. So we can equate that a change in energy to a change in wave vector, and this essentially from the definition of the velocity becomes that. And the change in energy can also be under an external electric field can be written as this. This is basically the work done by the electric field in a time delta t. And now I can use those equations and write my delta k as this. Please write this down and do the calculation yourself, otherwise it will be difficult. And I can now write the force as h cross dk by dt. So now I have an expression for which resembles Newton's law, but it should be understood that the momentum here is the crystal momentum. The rate of change of momentum is equal to the external force, but it is not the total momentum. It is only the change in momentum because of the force. The total momentum means you have to consider the change in momentum due to the ionic potential and so on. That is something that is extremely complex to do, and we assume that is not necessary. We will just consider that part of the momentum, which is the crystal momentum, which will change due to the external force. And that's why the concept of a crystal momentum is convenient. It helps us study the influence of external agencies. Now, in the presence of the magnetic field, the force equation becomes this, which is obviously well known, and I can plug in the expression for the velocity here. So if you look at this, the direction of the electron in the presence of a magnetic field would be perpendicular to the gradient of E of k. Now this means that the electron moves on a constant energy surface. We know that the magnetic field doesn't do any work, so it cannot change the energy of the electron. Therefore, because of that expression, it implies that the electron moves on a constant energy surface. Now given these expressions which we shall use, there are several assumptions made here. We are going to assume that the electron is confined to a single band. That is, the applied electric field or magnetic field is small and does not cause a transition from one band to the other. That is, interband transitions, they are not allowed. That is within our framework. And like I said before, the momentum is only because of the external fields and not the total momentum. Also, we are assuming that any energy given to the system is much less than the band gap of the system. Again, that is also another way of saying interband transitions does not happen. That is, if you apply more energy than the band gap, then electrons from the lower band can excite themselves to the higher band and so on. That doesn't happen in our framework for the moment. And again, as mentioned, we are working in the situation where the wavelengths of applied electric and magnetic fields are much greater than the lattice constant. And because of the periodicity, if I have a set of quantum numbers for the electron, or a set of parameters, n, the band index, the position, and the wave vector, if I shift the wave vector by a reciprocal lattice vector, then nothing changes. That's the definition of the periodicity of all the properties of the electron. So we are also, as we saw in the previous class, all distinct wave vectors of a single band can be found within the first Brillouin zone. That is the first Wigner-Seitz cell in the reciprocal space. And we will also assume that the Fermi-Dirac distribution applies, although in this course, so far, we have only used the Fermi-Dirac distribution at T equal to 0. You can use it at any temperature. Of course, when you do the StatV course, you will understand what is the full temperature dependence of this distribution. Now, we saw when we calculated the density of states, one allowed value of K corresponds to a volume of 2 pi by L, the whole cube. And this volume element in K space, so if I consider some volume element dk, then that dk will have dk divided by 2 pi by L whole cube allowed values of the wave vector. So one wave vector can be found in a volume given by this. When I say volume, it must be understood I'm talking about volumes in reciprocal space. So one wave vector has got a volume of that size. So if I consider some arbitrary element dk, then that will contain this many allowed values of k, and I can now write that the number of electrons per unit volume corresponding to dk is just that. Now, I can define the electrical current like this. We just saw this is just NEV, which is a form of Ohm's law. I can convert it into an integral like this, and then the thermal current can be written as N into energy into velocity. This form we had used in the previous class to find out an expression for thermal conductivity. So if you are worried about this form, you can go back and check why it is N into energy into velocity. I can rewrite that as an integral like this. Now, if I plug in the expression for dn, now the dn is basically basically this is dn, dk by 4 pi cube. That's the density of states in expressed in the momentum space. Earlier we saw the density of states in terms of energy, but this is just in the momentum space. So this is basically dn. dn is number of electrons per unit volume corresponding to dk. So that dn basically is this dk by 4 pi cubed, and then you have the expressions for the velocity plugged in, and again for the energy and the velocity I can rewrite that as this. So now there's something interesting here. Now here this integration you need to do just over the Brillouin zone, because all the relevant wave vectors are found inside the Brillouin zone, and you just need to integrate it over the Brillouin zone. Now let us consider the shape of this d by dk in one dimension. So this is the energy band in one dimensions on the top frame, or you have the same picture here. This is ek, and if I take the velocity, which is the gradient, I need to calculate the slope. That will be proportional to the velocity. The velocity will look like this. It's a very interesting shape here. We will consider that when we look at electric fields, but that's the shape of the velocity. But so I'm now integrating d by dk. So I'm now integrating this shape over the first Brillouin zone. Automatically you will understand that this will be 0. That integration will be 0. This integration will also be 0. So this follows from a theorem that if I have a periodic function and I find out its derivative, if the derivative of it squared, then the integral over the first Brillouin zone will be 0. In one dimension, it should be obvious that if I find out the integral of this velocity, it will be 0. But it's not 0 all the time. It is 0 only when all the states are filled. If all the states are filled in the energy band, and then the corresponding velocities will be this. Half the electrons will have positive velocity, half the electrons will have negative velocity. Effectively, there will be no current. So that means that if there is a fully filled band, then the current, which is just this integral, will be 0. All the electrons, half of them will have positive velocity, half of them will have negative velocity. They'll just cancel off. There will be no current. There will be no electrical current or thermal current. Now, if I have a partially filled band, that is, if I have in this energy band, if I have only states up to this point filled, so from here to there only filled, and there are small empty states here and here, then there will be a net current in the presence of thermal gradient or an electric field. So only partially filled bands contribute to electronic properties. On fully filled bands are inert. You don't need to consider fully filled bands at all. Now, in the Drude model, here Drude assumed that conduction bands were valence electrons. Now, there was no proper justification for this. The reason why it turns out to be right is because if you consider valence electrons, like for example in the case of sodium, we saw that in the previous video, end of the previous video. If I have just one electron per primitive cell, then the band will be half filled. Then there will be no space for the electrons to get accelerated into the empty states. So that's a half filled band. So then there will be conduction. But if it's a fully filled band, then there will be no conduction. So this is extremely important, that only partially filled bands contribute to electronic properties. So now we can go on to study a little more about why you have this kind of, for example, in the case of a semi-metal, there is a band overlap. And if you notice here, in this case, the bottom band is fully filled except for a small region here, and the top band is fully empty except for the small region which is filled here. Now, you may have studied from school that in this kind of a situation, I can consider, instead of all these electrons moving, I can think of the empty states here moving in the opposite direction, and that's called hole conduction, and this is electronic conduction. So we can consider, we can study why you have why this is necessary and how this band overlap comes as well. So that's what we're going to do now. We're going to look at band structures of an electron in a 2D lattice and appreciate how these things come about in the next video.